In this example, we're going to solve the following polynomial inequality. The inequality is x cubed plus 8x squared being less than 0. So we'll start by collecting all terms on the left-hand side and factoring the left-hand side as much as possible. So out of the two terms, out of x cubed and 8x squared, it's possible to factor out x squared. So we end up with x squared multiplied by x plus 8 being less than 0. And now we switch to the graphing approach to the inequality. So this expression being less than 0 is equivalent to the graph of y equals x squared multiplied by x plus 8 being below x-axis. So the wording below x-axis corresponds to the sign, the left-hand side being less than 0. And it's easier to determine where the graph of y equals x squared times x plus 8 is below x-axis. To do that, we'll determine the x-intercepts and multiplicities, and then make a sketch. So for x-intercepts, we set x squared times x plus 8 equals 0. So that splits into x squared equals 0 and x plus 8 equals 0. So then the first boils down to x being 0, and the second boils down to x being equal to -8. And for the multiplicities, the x equals 0 has multiplicity 2, and x equals -8 has multiplicity 1. So multiplicity 2 comes from x squared, and multiplicity 1 comes from x plus 8 being to the first power. So if the x-intercept is of odd multiplicity, the graph will cross x-axis at that point. And if the multiplicity is even, the graph will just touch x-axis but do not cross. So now we're going to graph the behavior of the polynomial using some test points. So put the two x-intercepts, x equals 0 and x equals -8. And then we use some test points. So here we need only one test point, x equals 1. So at x equals 1, we get y of 1 equals 1 squared multiplied by 1 plus 8. That's equal to 9. So it's a positive number. That means the graph is above x-axis at x equals 9. So the graph will be above x-axis between x equals 0 and the right hand of the graph. And then it's enough to determine what happens on all other subintervals. Since x equals 0 is a multiplicity 2 intercept, the graph will only touch x-axis. So it's going to be above x-axis, and it's going to stay above x-axis to the other side of x equals 0. So between x equals 0 and x equals -8, we have the graph being above. Then x equals -8 is a multiplicity 1 intercept, so the graph is going to cross over. So it was above on one side, so it's going to be below on the other side. So having all that information, we can make a rough sketch of the graph. So it stays below x-axis, then it switches above, bounces off, and goes above x-axis. So, and we're looking for the places where the graph is below x-axis. So the answer to the inequality being less than 0, the answer to the graph being below x-axis is the interval between 0 and -8. So we have that the graph is below x-axis on -∞, -8. So solution set to the inequality being less than 0 is -∞, -8. In this problem, we're going to solve the following polynomial inequality. The inequality is 3x cubed less than -15x squared. So we start by collecting all terms on the left-hand side and factoring the left-hand side as much as possible. So by moving -15x squared over, we end up with inequality 3x cubed plus 15x squared being less than 0. And then what we can factor out, both of those terms contain 3x squared. So I'm going to factor that out. When we take 3x squared out, we're left with 3x squared times x plus 5 being less than 0. So this inequality is equivalent to the graph of y equals 3x squared times x plus 5 being below x-axis. So the wording below corresponds to the inequality being less than 0. So to determine where the graph is below x-axis, we find x-intercepts and their multiplicities. So we set 3x squared times x plus 5 equals 0. So we get 3x squared equals 0, or x plus 5 is 0. That gives us x squared equals 0, or x equals negative 5. And this boils down to x equals 0, or x equals negative 5. Since the x equals 0 intercept comes from the x squared term, the multiplicity of that will be 2. And since intercept x equals negative 5 comes from x plus 5 to the first power, its multiplicity is 1. So at the even multiplicity intercept, the graph only touches x-axis, and at the odd multiplicity intercept, the graph crosses x-axis. So now we're ready to graph this with test points. So negative 5 and 0 are the two x-intercepts. So we could use some test point. This time we're going to use x equals negative 6. That's our test point. So y of negative 6 is equal to 3 times negative 6 squared times negative 6 plus 5. We calculate that out, we get negative 108. So since it is a negative number, it means that the graph is below x-axis. So between left hand and negative 5, the graph is below x-axis. And then we go by each intercept. Since negative 5 is the degree 1 intercept, its multiplicity 1 intercept, the graph will cross the x-axis. So on the other side of negative 5, the graph should be above. And then at 0, the graph only touches x-axis, so it was above on one side, so it's going to stay above on the other side. So we're looking for the places where the graph is below x-axis. So this is the schematic representation of the graph. So the graph will be below on the interval between negative infinity and negative 5. So the graph of y equals 3x squared times x plus 5 is below x-axis on the interval negative infinity, negative 5, and that's exactly the solution set to inequality. So the answer to the inequality is interval from negative infinity to negative 5. In this problem, I'm going to solve the following inequality. The product of 2x minus 1, 3x plus 2, and x minus 3 is greater or equal than 0. I'm going to start by collecting all terms on the left-hand side and factor in the left-hand side as much as possible. Well, it is already done for us. So if you re-examine the inequalities, so this left-hand side being greater or equal than 0 is equivalent to the graph of y equals 2x minus 1 times 3x plus 2 times x minus 3 being above or exactly on x-axis. So to determine where the graph is exactly on or above x-axis, so find x-intercepts and multiplicities. So set the entire expression equals 0. So that splits into 2x minus 1 being 0, 3x plus 2 being 0, and x minus 3 being 0. So that gives us x equals 1/2, x equals negative 2/3, and x equals 3 for the x-intercepts. And multiplicity of each of those intercepts will be 1, because each of those parentheses is only to the first power. So what we're going to have, we have that the graph crosses x-axis at each of the 3 x-intercepts. So we're going to make a sketch of the graph using test points. So here's the number line. We label the x-intercepts, negative 2/3, 1/2, and 3. Then use some test points. We're going to use the convenient test point x equals 0. So if we calculate y of 0, we're going to end up with -1 multiplied by 2 multiplied by -3. That gives us +6. So that means the graph is above x-axis at that point. So between -2/3 and 1/2, the graph is above x-axis. And then, since the graph is crossing x-axis at each x-intercept, to the other side of -2/3, the graph is going to be below. And then to the other side of 1/2, the graph is going to be below. And to the other side of 3, the graph is going to be above. So schematically, this is how the graph of the polynomial looks like. So going back to the inequality, we're looking for the places where the graph is above or exactly on x-axis. So for the above pieces, we have the interval between -2/3 and 1/2, and everything to the right of 3. So we have that the graph of y equals to x minus 1 times 3x plus 2 times x minus 3 is above or exactly on x-axis on the intervals -2/3, 1/2, with square brackets, together with the interval from 3 to +infinity with a square bracket. So that gives us the solution set to original inequality to be exactly the same collection of intervals. So it's -2/3, 1/2, together with 3 up to +infinity. And we have square brackets next to all finite points.